A data manifold is just the shape that data tends to lie on when you plot it in a space. When you represent that set of objects as points, as feature vectors in a space, they're going to have some non-random, non-uniform distribution in that space. And this is an idea that I think underlies practically all of data science and machine learning. In machine learning, you can train a model to essentially memorize the structure of this data manifold and then make decisions based on that. Literally any type of data that's drawn from the real world or even a simulation is going to have some kind of structure to it. As I'm going to show in this project, it turns out to be especially true when it comes to music. I think we can all hear that there are patterns in music. There are repeating sequences, there's like transitions between the different parts of a song. There's layers of instrumentation that kind of get added and then taken away. Can we use deep neural networks and deep learning frameworks to help visualize how music evolves over time? There really aren't that many ways that I found to visualize music. You can plot the sound wave itself. If you have access, you can look at the digital audio workstation and look at how the producers actually put those tracks together. None of these really capture how the music transitions between its parts. We'd like to be able to intuitively hear that there's some change going on in the music and then see a corresponding change in some visual object that represents that music. I'm going to show a simplified version of this model I built where we're only really concerned with what's called the embedding step. And that's where we're going to take the raw audio and transform it into a path. This is the embedding step. So we're going to start with a raw wave file where you're looking at the sound wave. I used Python and we're going to convert this to a spectrogram image where you have time on the x-axis and then frequency. This is done through Fourier transforms, so the details of that are not really important, but at every point in time you get a reading of what frequencies are kind of present that compose the signal at that point in time. This little box here, we're going to slide this sliding window across, just like a train car moving down the track. At every discrete interval, we're going to take a snapshot of that image, that sub-image, and we're going to feed this to an encoder network. This is going to be a one-dimensional convolutional network. Through multiple layers of processing, it's going to compress this down into just 3 numbers, x, y, z coordinates. This is an actual trajectory from a clip from one song. You can see these 3 different sets of rings here, the large, the medium, and the small, and those different groups of rings kind of corresponded to different moments, different sections of the song that were qualitatively like distinct from each other. This encoder network is really just one component of the larger model. The simplest possible version is that it's just an autoencoder. This is a diagram of a 2-dimensional convolutional autoencoder where you have an image come in, you're convolving the image with convolutional kernels and forming a different representation of that input, and then you're also following that by downsampling the spatial dimensions. What was in that window gets compressed down to a single small vector at the middle of that bottleneck. That small vector is then given to a decoder that does those operations sort of in reverse, where it's performing convolutions but also like upsampling the spatial dimensions. As you train this network to reconstruct the input that it was given, you end up forming at the middle this really nice compact representation of that input. I'm now going to show what happens when we use this algorithm to embed different pieces of music. I'm first going to show this one set of 6 songs. Each clip is about 25 seconds long. Just watch that point as it moves down the track and just listen very closely. It takes a little bit of getting used to, but you'll start to see why the embedding is shaped the way that it is. Similar sounding moments are going to be placed near to each other in the space, while different sounds are going to be placed further apart. If you think about it, the fact that they have that kind of bird's nest annular shape makes a lot of sense. They really start to look like what are called strange attractors, if you're familiar with the dynamical systems theory. I used a sliding window of 0.5 seconds. 0.5 seconds is going to get mapped to a single point in the three-dimensional embedding space. You can imagine with that representation, it's going to have difficulty differentiating an entire verse from the chorus. What it did instead, it seems, is to actually just differentiate the bass drum from the snare drum. And I did play with using like a 2-second window, which is 4 times longer, and that dramatically changes the shape. It makes it a lot smoother. This one you're seeing is for the classical piece by Vivaldi that we're gonna see next. So now let's check out the second set where the embedding is not so dependent on the cyclic patterns in the rhythm.
Would you smoke this again?
Yes.
Yeah.
I would,
In
definitely.
a darkened room with a good book or...
It's a night cigar.
Yeah. Nightcap. Last cigar of the day? Bit light for that?
I think it's picking up power. It's definitely picking up power.
If you're interested in learning more about this project or want to implement it yourself, I wrote a good-sized blog post that I'll link below, and I posted the code on GitHub repository. And I actually started this project working with video data, and I put that code in a different repository. It's very similar to this model, but just the input, the original input is changed from like a 1D continent to a 2D continent, and then everything after that is identical. Yeah, so with that, thank you for listening. Bye-bye.